Hi everyone, and welcome back to Spaced Out. So today we're going to be talking about the moon, how it formed, and why it plays such a huge role in life on Earth. So why does the moon even matter to us? Other than being a pretty object in the sky, close enough to photograph during an eclipse, or even look at through a telescope, does it really do anything? Well, yes, quite a bit actually. First, and most obviously, without the moon, the night sky would be much darker. The moon doesn't produce its own light, but it acts like a giant mirror, reflecting sunlight, and that's why we see it glowing so brightly at night. And during the day, it can still be up there, just washed out by the sun's glare or below the horizon, depending on the time. But that light isn't just beautiful, it's really important. Many nocturnal animals rely on the moonlight to hunt, navigate, and survive. Without it, entire food chains could collapse and species might even go extinct. And that's just the beginning. The moon also plays a huge role in shaping the Earth's environment, especially when it comes to seasons and tides. Let's start with seasons. Earth spins on a tilted axis, not straight up and down. It's tilted at about 23.5 degrees. This means that one side of the Earth is always tilted more towards the sun than the other. Now, when the northern hemisphere is tilted towards the Earth, it's summer there. When it's tilted away, it's winter. And that's why the northern and southern hemispheres have opposite seasons. Now, here's where the moon comes in. The moon acts like a gravitational anchor. It helps keep the tilt stable. Without it, the Earth would wobble much more due to gravitational tugs from massive bodies like the Sun and even Jupiter. Even though the moon is much smaller than either of these objects, it's much closer, and its closeness makes its gravitational influence on Earth surprisingly strong. Now, scientists have run simulations that show that without the moon, Earth's tilt could swing anywhere from 0 degrees, meaning no seasons at all, to 90 degrees, where the poles would point directly at the sun at all times. Now, imagine one pole baking in constant daylight while the other freezes in darkness. This kind of climate chaos would make life, at least as we know it, incredibly difficult, maybe even impossible. Now, let's talk about tides. Tides happen because the moon's gravity pulls on Earth's oceans, causing the water to bulge. One bulge happens on the side facing the moon. That's the part being pulled. Now, the other bulge, that's on the opposite side of Earth and happens because of inertia. That side is kind of like what happens when you're going around a merry-go-round. As the whole merry-go-round spins, you feel a force pulling you out of the merry-go-round, which is why you hold on to something when you're on it. Now, that outward motion is the result of the spinning motion. On Earth, the ocean opposite to where the moon is behaves like this. It's not being pulled outward by the moon directly, but it's flung outward as the Earth spins. As the Earth rotates, different parts of the planet move through these bulges, and that's why we experience 2 high tides and 2 low tides every day. But the tides do much more than create fun waves to surf on and swim with. They stir up nutrients from the seafloor, helping oxygen move deeper into the ocean, and even drive really large-scale ocean currents. Now, the circulation helps carry warm water from the equator towards the poles and cold water from the poles towards the equator, moderating temperatures and helping oceans stay alive and well. The moon really matters, but it raises a big question. How did it form? To answer that, we need to go back all the way to when the solar system was forming. Back then, the solar system was a violent place. Planets were forming from a spinning disk of dust and gas around the sun. And leftover material, chunks called planetesimals and protoplanets, were crashing into each other all the time. Now, one of these crashes was different. According to the giant impact hypothesis, a Mars-sized body, which scientists call Theia, collided with the early Earth. The impact was enormous. It melted both bodies, flung molten rock into orbit, and over time, the idea is that that debris came together to form the moon. Now, we have evidence for this thanks to the Apollo missions, which brought back hundreds of pounds of lunar rocks and soil. These samples help show that the moon must have formed around 60 million years after the solar system formed, right in the middle of that chaotic and collision-filled period. The rocks reveal a high concentration of anorthosite, which is an igneous rock that tends to float towards the top of a magma ocean. This tells us that at one point the moon was completely molten, which is exactly what you'd expect after a very, very high energy impact. The lunar rocks also contain very low levels of volatile elements. These are things like water or gases that evaporate easily when heated. That's another sign that the moon formed in a violent, high-temperature event, one that vaporized these materials and allowed them to escape into space, which is why we don't see them now. Even the moon's core is a clue. Earth's core makes up about 30% of its total mass, while the moon's is only about 2%. This suggests that the moon formed mostly from Earth's outer layers and Thea's crust, while the denser materials like iron sank into Earth's core. Now, scientists have considered other theories too, of course. The first is the capture theory, the idea that the moon formed elsewhere and got caught in Earth's gravity. That doesn't really fit what we see with the moon's orbit or its composition. The other is the co-formation theory, where the Earth and the moon form side by side, but that doesn't really explain why they're different. And the third big one is the fission theory, the idea that a fast-spinning Earth flung off part of itself. But that can't really occur for the moon's current orbit or its structure. So we were able to settle on the giant impact hypothesis because this best explains the evidence we see. The moon and Earth are chemically similar, but they're not identical, which makes sense if they came from the same region of the solar system and were once part of the same collision. And today, scientists even study lunar meteorites, bits of the moon knocked off by later impacts and found on Earth. These help give us a wider sample than the Apollo missions, which only collected rocks from one small region near the moon's equator. So, in the end, we conclude that the moon was born most likely out of destruction, the result of a catastrophic event that reshaped Earth forever. But from that destruction came something really important for life on Earth, a moon that studies our planet, helps stir our ocean, and make our nights a lot brighter, and probably one that makes life possible. If you're interested in more ideas of planet formation and how our solar system formed, you can check out my episode about planet formation on my channel. As always, thanks for listening to Spaced Out, and I'll talk to you next time.